Good morning, ladies and gentlemen. Welcome back to the second term. I hope you had a good break. Start off the term with chapter 5, almost where we left off in chapter 4. Heading there, joint probability distributions. It could sort of have been in brackets, math chapter as well, so double integrals and things like that. Very similar to the first sections in chapters 3 and 4. There are going to be a couple of statistical definitions. So what is the expected value? What is the variance? What is a conditional distribution when working with joint distributions? Most of those you will find in your formula sheet. Please have that with you. Once you've written down the statistical definition in our notation, then the next couple of equal lines is going through your integrals, going through your summation, basically sitting down and doing the maths. I will do that in our Thursday session when I go through examples for this chapter. In here, for this theory note section, document rather, just show you what those different equations are, what they mean, and why do we have them. And again, please have your formula sheet with you. So a joint distribution, as the name suggests, now we can directly ask a probability question about two variables. So X could be temperature, Y could be time or something like that. And we want to know a specific probability. And the way that we write this, you see a little sub X and sub F, X and Y there at the bottom. And in here the value. So if I write this, say 5 and 7, that is probability X is 5 and Y is 7. Just give me a second, I've got a 2-year-old knocking on the door. Sorry about that, an excited 2-year-old telling me she's walking to the park next door. So that notation that you see there, you want to know what's the probability. X is 5 and at exactly the same time Y is equal to 7. We can have a joint mass function. Remember mass, where we add things together. We can have a joint density function where we integrate together. Same definition as in chapters 3 and 4. Everything added together must give me 1. Everything integrated together must give me 1. So at the end of the day, the only difference for you guys going from 3 and 4 up to chapter 5, you're going to have double summations we may need to solve, or, and this is where unfortunately a lot of students fall out of the bus, you're going to have a double integral that you need to solve. I've mentioned this in chapter 4 as well. This is not a mathematics course. So the types of integrals I will expect you to be able to do, you would have done examples of those somewhere in the course, be it textbook examples, tutorial questions, or examples I will do in class on Thursdays. If you do get stuck with an integral, if you are doing, for example, a textbook example and it's taking 20-30 minutes, please ask myself, post a question on Sunlearn, ask one of the demis. Before you go too far, just make sure it is a question I can actually, well, not can, question I will ask you. I don't want you spending 20-30 minutes on doing an integral. That is not the aim of the course. You will get 1 mark for the first line, writing down the statistical definition. You will get 1 mark for the final answer. And then the middle bit, the maths bit, I'm not really that interested in. 1 or 2 marks depending on the length. But for this course, line 1 and the final answer, the 2 important bits. 2 ways this can be presented in a little table. So this is a mass function. Looks like that. You can see the individual probabilities for, let's say, Y is equal to 1, and at the same time X is 2. That will be the 0.210 that you see there. Example 5.2. Let me just turn to my textbook here. You will see an actual equation. So that is a joint density function. So in example 5.2, we have time until a computer server connects to a machine, y until the server authorizes you as a valid user in milliseconds. So it's the total time that it takes for you to connect and then time to get authorized. So the bottom one, this is a density example. Density, we get our probabilities by integrating. The top one, this is a probability mass example, and here you will just add values together. So if you want an individual probabilities, the top one, let's say x is equal to 3, y is equal to 2. Well, if I have a table, I don't really need to do that much. x3, y2 is there. I can't ask you a question like that in the density setup. Remember, in densities, the probability of being equal is just 0. So in a density, you would end up with a question something like less than 3, y less than 5, for example, something like that. And you would then need to integrate depending on where x starts. Let's just say minus infinity to 3 and minus infinity to 5. So significantly easier in the top case, as mass functions are. You just add together. Density, it adds the slightly more complication in the sense that we have to integrate things together. And there, please don't let the integration cost you any marks. You shouldn't be losing mathematics marks, if ideally not to lose any marks, but if you do lose marks, at least you lose statistics mark. But don't have the first line correct. So this is the statistical bit, this bit. X is less than 3, y is less than 5. First integral, second integral, you write your density function there, dx, dy. This, in my mind, is what I call the statistical definition, or the statistical way of doing it. After this, you've got a couple of equal signs where you now go into the mathematics to get an answer. I'll look at a bit more of these in Thursday's class just to show you what I can expect of you. Immediately on that note, and I think there is a little bit in the notes section for this document as well. So if you look at the study notes for this bit at the bottom of the slide, if you have the PDF version, look at the bottom of the slide, you'll see there's a little notes block. In there I mentioned this as well. Example 5.2 in your textbook is more complicated than what I can ask you, and that is part of the reason students have issues with this problem. And the reason for that, if you look very carefully in your textbook, you'll see they give you the function and then they say, and this is the annoying bit, for x less than y. So that's the definition area for x and y. And that means a lot of the integration that you do, you actually run into a little bit of a problem. Because of this, for this question, what happens here, that must actually be an x. Because y must always be larger than x for this specific example, this is not a general thing for any density function, for any joint density function. It's purely the textbook. For some or other reason, I don't understand why they would put such a difficult mathematics example in the textbook. But this is why whenever you look at the integrals for this example, you will see the second integral always starts at x. Nothing to do with statistics. It's purely because of the fact for this example, they define y as being larger than x. Now it's got to do with connecting to a computer and then you being authorized. You can't be authorized before you've actually connected. So it sort of makes sense there. If it takes you 3 seconds to connect, well, you first connect and then you authorize. You can't be authorized in 2 seconds. If it takes you to connect, it takes 5 seconds. So, but I would have had a slightly easier example here. But this is why, just keep your eye on this when you work through example 5.2 and its subsequent examples going through this whole chapter. This is where it becomes annoying. But in Thursday's class, I will tell you, or I'll show you the examples that you can expect for this course. Now our definitions. We have something called the marginal distribution, and it gets its name from the fact that it's literally the margins in the table. This is your row margins, and in this case this is X, so this is actually X's distribution. 2, 3, 4, so there are my options, and there you get your probabilities, 0.71, 0.09, 0.185. So this is X's marginal distribution. How did we get it? You add up all the values in the row. We have the column distribution, so Y's distribution will be your column margins. Gives me Y's distribution. So you add up the values in each column. The column totals are your individual probabilities. So for Y, the probability of 0 is 0.272. Probability of 1, 3, 4, 6. 173 is the probability of 2, and the probability of 3. For X, 716, 09, 185. So now from the joint distribution, I can actually write down the two individual marginal distributions, is what we call them. Example 5.4 shows you how you do that in integrating out the function. And immediately, as I said earlier, please be careful with example 5. Let me just get my textbook to there. Please be careful with that example. It's more difficult than it needs to be because of this annoying thing always having to start integrating from X. In class on Thursday, I will show you a slightly better example. No, better is not the right word. There's nothing wrong with example 5.4. It's just more difficult than what it needs to be for the purposes of your assessment A2 and A3. Let's put it that way. So marginal distribution, first definition you should have written down somewhere on a piece of paper. Next one, we have something called the conditional distribution. So the conditional distribution is a distribution for specific X value. So what's the difference between this is the general distribution for Y. So that's Y's marginal distribution or just Y's distribution. This that you have there, I set X to be a specific value. Now I want to know what will Y's distribution be. So in our table on the previous page, now I can't turn the page when making these documents, but on the previous page, if I tell you X is equal to 7, X is equal to 1. So I'm setting one of the rows fixed. What are my possible Y values now? That will be the conditional distribution. And for purposes of this course, whenever I ask you this, so the statistical bit that you write down, that is its definition. Distribution of xy divided by distribution of fx. It will also integrate out to 1 or sum to 1. It must always do that. And it is a fully fledged density function on its own. So for different values of the one variable, I can figure out what the distribution is of the second one. Now in practice, where may you use this? A lot of manufacturing, for example, is temperature dependent. So you set a specific temperature, that's your one variable, x. You want to know what will y, let's say, is the distribution of your tensile strength of your steel or something like that. So you've got a joint distribution, the tensile strength and the temperature that you produce at. So that would be your fxy. If you want to know for specific temperature, you're going to use 500 Kelvin or 700 Kelvin or whatever the temperature is you're going to work with. What will the the distribution of my tensile strength be, then it's this one. So this distribution of my tensile strength, irrespective of the temperature. So it's sort of an average distribution across all different temperatures. This will be for a specific temperature. So now I'm producing at 500 Kelvin, 500 Celsius, 500 Fahrenheit, whichever temperature you prefer working with. What is the distribution of my tensile strength now? So it's just a definition you need to get right, the difference between a red and what is that, an orange yellow color. Now because this is a fully fledged distribution in its own right, it as a distribution has an expected value and it has a variance. So once you get that, expected value is integral of y times that, the variance similar to what we did before, y squared minus the expected value. Conditional distribution is just slogging through the maths to be perfectly blunt. You get the distribution, so you first do this. Once you have that, I can ask you expected value and variance. So if I set the temperature at 500 Kelvin, what is the expected strength of your steel? If I set the temperature at 500 Kelvin, what will be the variance of my tensile strength of the steel? Those two. And on here you see examples of both. Again, please have your formula sheet with you. Don't go and memorize things if it's not needed. These are in there. You have examples of these in those different sections, taking you through all of this to actually go and get those answers. Section 5. What's this? 5.2. And there is, to be honest, no quick, easy way of doing it. You just slog through the maths for all of these problems, for all of these examples. No quick way, no roundabout way, no easy shortcut method or anything like that. You write the definition and then you follow and you do the maths. Next definition, independent. Two distributions are said to be independent if we can split them up like that. So if the joint distribution is the product of the two marginals, then we'd say that these are independent. Then your conditional distributions also just the same. So where does this come from? If you remember back to chapter 3, independence. That's one definition. If that's true, they're independent. Also, A given B equal to A. It's another way of showing something's independent, or B given A equal to B. So the three lines that you see on this slide in terms of distributions, just a continuation of those three definitions we had in chapter 2 when we defined independent events. Very nice to have. So if we can have this property, it makes my life significantly easier when doing calculations. Often overused in practice, people tend to assume independence when it's actually not the case. So it's something we need to prove. How would you prove this? You would calculate these two individually. So get that one's answer, get that one's answer, then multiply them together and see if you can get the joint distribution. It's not something we ever reason out. We let the maths do the talking. If I can show that to be true, multiply them together, you get the joint, then these events are independent. Be on the lookout for this. If I tell this to you somewhere in a question, I can sort of gloss over the fact there's one little bit somewhere in the sentence. I give you a whole paragraph of background information. This is X, this is Y. And then somewhere hidden away in that paragraph, X and Y are independent. And if you misread that, you don't figure that out, then some of the questions A, B, or C you may actually not be able to do because it would need this independence. Last concept for this chapter, covariance and correlation. Covariance, how do these two variables vary together? And the idea is, it tells us, gives us an idea of the association between the two variables. Now we have two values. We have a covariance and we have a correlation. The covariance we don't like to use because it has a unit problem. The covariance, if X is, let's say, centimeters and Y is Celsius, your covariance, the unit for the covariance will be centimeters times Celsius, which has absolutely no meaning. So the covariance, although that's the one we start off with in terms of our calculations, similar problem to the variance, notation, units, very difficult to calculate. So a better version, it's a slight change to it, the correlation has no units. The correlation, it's a value between -1 and +1, that's it. So that is a lot easier to interpret. As soon as something is bounded, I can tell you it's close to a boundary or not. So you can say if something is big or small. The covariance is not bounded. A covariance of 20 billion may be small. It depends on what your values are that you're working with. A covariance of 5 may be large. It depends on the values that you're working with. So the covariance, not easy to interpret. When is it big or small? What are the units? So a lot of hassles with it. Correlation, we overcome some of that hassle because it actually has no unit, bounded between minus and +1. Positive values for both of these, if your covariance or your correlation's positive, it means they move in the same direction. So if your one variable goes up, the other one will go up as well. If it's negative, the one goes up, the other one goes down. Now that may be a good thing to know in practice, especially the negative one. If the covariance or the correlation in my factory between temperature and tensile strength, if they are negative, that means to get stronger steel, I actually have to reduce my temperature. If they are positive, so tensile strength and temperature in your joint distribution, if they are positively correlated or positive covariance, that means if you increase the temperature of your production, you would also increase the tensile strength. So that's the big takeaway from these two, is if I change the one value, so if I increase the one value, will that increase or decrease the other one? And our last slide is how do we actually calculate these values? The one thing on here I just want to show, well, two things. That standard expected value and expected values from expected value of X, that's the expected value of Y, there, hidden away somewhere there. That is the standard deviation of those two. So that we can get. You need the individual marginal distributions. This expected value of xy, integral over x over y of xy times the joint one. And that's sort of what that one comes down to. So the expected value of anything, so in our case it's just an x and a y, you take that function, plug it in your integral, and times by the density function. So this red one is a new one on this slide. So this takes a while doing. You take the x and the y, you multiply it in there, and you get your end result. This, if I ask you for a covariance, or for example a correlation, it's 3 or 4 pages of maths that you just struggle through. Well, not struggle, hopefully not struggle through, that you just work through, better way of putting it. This is the notation for the correlation. So that's the correlation. That is the covariance. Covariance. So those are the two notations we have. Sigma xy is the notation for covariance. Rho, this is the Greek letter rho, R in the Greek alphabet. Xy is the correlation coefficient. You can see you take that value and you divide by 2 standard deviations. Now what happens here, this one's unit will be centimeters and Celsius. This will be centimeters, that will be Celsius. All of this cancels out and you're left with something that's just a value between -1 and +1. You can go and prove that mathematically. So no units, no anything. So the correlation coefficient is always a nice one to work with. So in this Thursday's session, 10 to 12, I'll go through the stats part, which is a minimal part of this chapter. It's really just knowing these definitions. More importantly, on Thursday, I will show you the types of maths in terms of integrating and things like that, that I can expect you to do in this course. Thanks a lot.